Hi, my name is Niny Arcila-Maya. I'm a postdoc at Duke University. And today I want to talk about topological Azumaya algebras, which is a topic in algebraic topology. The idea is that they arise as a generalization of central simple algebras, which is a purely algebraic concept. And what I studied in my dissertation was what conditions can we impose on these objects so that a structure theorem that we have for central simple algebras also holds for topological Azumaya algebras. So let's get started. A topological Azumaya algebra is going to be a bundle of complex algebras, so that when you look at it locally, then it is going to look like a matrix algebra of degree n, right? So we have our base space, our point in the base space, and the fiber is isomorphic to the matrix algebra of degree n. As examples, we have, well, the trivial bundle. Another example is that if you start with a complex vector bundle of rank n, then by taking the endomorphism bundle of this complex vector bundle, then that's going to be a topological Azumaya algebra of degree n, because you will be taking endomorphisms of C to the n, which gives you exactly your matrix algebra of degree n. Okay, the set of these new objects is going to be endowed with an operation, which is a tensor product operation. And the way it works is that you are going to take a topological Azumaya algebra of degree m and another one of degree n. And to produce a new topological Azumaya algebra, you're going to perform the operation fiber-wise. So you're going to take the fiber of the first one and you're going to tensorize it over the complex with the fiber of the second one. The reason why this works is because tensor product of matrix algebra is again a matrix algebra. So that means that when you start with a TAA of degree m and tensorize it with a TAA of degree n, you are going to obtain a TAA of degree mn. Okay, so now we have this new object and operations in the set of this new object. So in the theory of central simple algebras, we have a structure theorem that says that when you start with a central simple algebra whose degree has this prime decomposition, then you can break down this central simple algebra in smaller pieces of central simple algebras, where this decomposition is nice in the sense that each of those pieces have dimensions, or well, degrees, I mean, that correspond to the prime factorization of the degree of the bigger one. A very natural question to ask is, as TAAs are generalizations of this concept, would we have such decomposition theorem in the theory of these new objects? And well, Salman actually asked this question. He asked where we have prime decomposition, that's how you call it, for TAAs under the tensor product. The answer to that question is negative. So in general, there is no such decomposition. Antio and Williams came up with a counterexample in 2014 where they found a CW complex that has dimension 6 and a topological Azumaya algebra of degree 2 times an odd integer, so 2 times n. And they showed that that A can never be decomposed as a topological Azumaya algebra of degree 2 tensor product 1 of degree n. So after that answer, then another question that comes up is, okay, if that's not true, then what conditions can we impose on these integers? Let's say integers m and n, so that a topological Azumaya algebra of degree mn can be broken down into two pieces, one of degree m and another one of degree n. Well, one of the results from my dissertation says that you will need m and n to be relatively prime, and you will need X to be a CW complex whose dimension is bounded by 2 times the smallest integer plus 1. Then when that happens, the decomposition will happen. The way we can prove this, one strategy is, first we think of TAAs as homotopy classes. Then we understand this problem in terms of homotopy. And once we do that, a lifting problem comes up. So the third step is solving that lifting problem. The heart of the proof of this theorem lies on the third step, but I will quickly tell you what the other two steps are about. You think of topological Azumaya algebras as homotopy classes by using these bijective correspondences. So at the end, topological Azumaya algebras will be like the set of isomorphism classes of them will be in bijective correspondence with pointed homotopy classes of maps from X to the classifying space of the projective general linear group. So we will now think of TAAs of degree n as these maps, well, classes of those maps. Now, once you do that, you need to rewrite the tensor product in these new terms. The way you do it is you start with the Kronecker product of matrix algebras. That product behaves nicely in terms of the center, meaning it sends the center to the center. That gives a tensor product at the level of projective general linear groups. Then we take the classifying space functor of this homomorphism, and we have now a map at the level of classifying spaces. This map is useful because it will relate the classifying spaces that we need. So what happens is that if you start with two topological Azumaya algebras of degrees m and n, then you are going, that means you have this map here. And then you will compose it with our F tensor, and that will result in this map here from X to the classifying space of the projective general linear group of degree mn. And then that's your tensor product. Good. Now in these terms, our problem of decomposing a topological Azumaya algebra becomes then a lifting problem. So if you start with your A that has degree mn, you want to find these two of degrees m and n so that this diagram commutes up to homotopy. Okay. So the third part is, how do we solve this lifting problem? Initially, you would think that if we find a section of F tensor, that would solve the problem, and that's great, that would solve the problem. But there is bad news. That map, F tensor, does not have a section. So we need to use another approach. One that works is we create a section of F tensor in a range. How? Well, we come up with a space Y, and we come up with a function J, so that J and the projection fits in a diagram of this form. And because the projection has a section, then we compose the section with the homotopy inverse of J in a range. So this homotopy inverse in a range, and then that allows us to lift our function, and that's what produces the restriction in the dimension of X. And that'll be all. Thank you so much.